presentation is on quantum computing, codes, cryptography and cryptanalysis, QC4 by Professor C. Veni Madhavan sir. Professor C. Veni Madhavan sir obtained his academic degrees B. Electrical Engineering from College of Engineering, Madras in 1969, ME Control Systems from BITS Pilani in 1971, and PhD Control Theory from Indian Institute of Science in 1975. He worked in the industry, Air India from 1976 to 77, National Informatics Center 1977 to 1982, before joining the Computer Science and Automation Department of IISc in 1983. He was a senior professor in the Computer Science and Automation Department and retired formally in the year August 2014. He was the chairman of the CSA department during 1998 to 2000. He was invited to head the DRDO laboratory SAG, New Delhi during 2000 to 2003. His current research areas of interest are computational linguistics and pragmatic cryptanalysis. He continues to work in IISc on 3 R&D projects in the areas of cryptography and natural language processing, and on several technical advisory tasks spanning government policy, academia and research mentorship. He has worked on many scientific, industrial, consulting and development projects sponsored by government and corporate sectors in these areas. He has published over 80 plus papers in referred journals and conferences, and delivered over 200 invited talks in national conferences and universities. He has guided 16 PhD students, 12 MS students and over 100 ME theses. He is the co-author of the book on public key cryptography published in India in the year 2009. He is the co-author of the recently filed Indian patent on a new encryption algorithm. An international patent is also in the process of being filed. Some of his project engagements were in the areas of cryptanalysis, cryptography and cognitive networks. He was a co-investigator in a multi-institutional consortium project funded by Sephira IFC PAR. The collaborative projects between IISc, TCS, University of Nice, France and Gemalto, France was on the design and development of various financial inclusion platforms on the mobile telephone infrastructure. He developed a system for handling e-cash and e-wallet applications based on a novel design and digital analog of denominational fiat currency. Sir used to call it as VM money, so that I remember that. He was the general chair of the conference of ATCOM 2017 of ACSC and the theme of blockchains and cryptocurrencies, and the chairman of INE Engineers Conclave 2001 on the theme digital economy. He obtained in 2001 an award of Mathematical Association of India for distinguished services in mathematics education and research. He obtained in March 2011 an award by IISc for excellence in research and engineering. He was an associate faculty at the Center of Neuroscience of IISc. He was the chief executive of the Society of Innovation and Development of IISc during 2006 and to 2012. He is closely associated with the activities of professional bodies like Cryptology Research Society of India, the Ramanujam Mathematical Society, ACS and INAE. He also works very closely with government policy and R&D funding panels of DST, MCIT, DRDO, NRB, NTRO, and with academic councils of universities of research centers like DSU, Sastra, Amrita, and as a member of technical expert committees. With this thing, we welcome you, sir, as a distinguished speaker to this event.
Right, thank you.
We request Dr. S.D. Sudarshan to kindly welcome sir.
Mr. Formal welcome now. Oh, okay. Thank you. That's part of it. Thank you. Nice being here. It's been a pleasure to be with CDAC for the last 30 years. I think more than many of the CDAC friends here, I've been part of many engagements with CDAC since 95, projects, reviews, panels, lectures, etc. So I will just take this 20 minutes.
Up to you, sir.
It could go on. See, this is about error control coding. I want to quickly give you a bird's eye view, capsule view of quantum error correction. A very important item in the agenda of the future of quantum computing, in particular with reference to cryptography. In particular, when I say cryptography, it's about cryptanalysis. Okay? All of this thing about quantum hype and hope will be there. And also quantum computing will be there, quantum computers will be there. They will solve a variety of things. They're already beginning to showcase such things in the major companies of the world. I'm not talking about the Googles and the IBMs. Several startups like QEra, IonQ, continuum, and our own 2 pi's, AI, and so on. So quantum computing will be there, will coexist with standard computing. High-powered quantum computers will be there with high-powered HPC, and so on and so forth. I doubt whether quantum computed mobile phone could be there, but Q dot-based television sets are already there, quantum dot-based things. Okay? So anyway, there's a whole lot of things about quantum magic, quantum computing, quantum sensing, quantum materials, quantum communication, which are going to fly. But quantum computing for breaking the threat to all of us in this conference related to digital signatures, etc., will be there, may not be there. And I have my pet joke. I'll close with that joke, which I keep hearing everywhere. RSA 2048 is not likely to be broken before 2048. Now, this is easy for you all to remember, the younger among you. When 2048, if I live, it will be probably 100, and I don't want it to be broken before I'm 100 years old. Either I'm not there, or RSA 2048 is not broken. Many reasons, many deep technical reasons, some of which I air. In all of these, quantum error correction is going to be central to quantum computing, and as I said, to cryptanalysis. And when I say quantum cryptography, I include methods from classical cryptography, which are going to come to the aid of quantum cryptanalysis, which is going to be protected by new classical cryptography, probably quantum resistant. I say probably because quantum algorithms to break post-quantum crypto of today are also in the air. They have not been successful with respect to the lattice-based things when the lattices are of certain sizes, not likely to remain, with probably side channels and other things. But that's why you already have code-based things resurrected, in particular for the alternatives, which are HQC, having quasi-cyclic codes, which are the second line of defense in case something happens to lattice-based stuff. So, these kind of maths and things will keep alternating. But as I just mentioned in the previous remark, there are lots of good old nice math in combinatorial math which have been tested out for post-quantum and even classical strong crypto. They have not flown because of the practical difficulties and so on and so forth. So this is the kind of world we are in. And in 15, 20 minutes, I'll try to capture the very exciting field to me of the quantum error correction. Okay, so now, sorry. Okay, so 14th April 4.14, it's written, is the first part of the constant of the Planck's constant, and that was declared as a World Quantum Day, and this year is supposed to be the quantum year, year of quantum science and technology. So like pi, 14th March, 14th April are all some celebrations to math and physics. Now, this is all based on a kind of a course I'm trying to build, and of course, and research related to that the last 1 year. I'm excited because there are so many important things, so many difficult things, so many interesting things, and they are all there, and these are the type of things I build on. But I'm now going to look at only the codes, and there are several things about codes. I'll just run through a quick capsule history. Quantum codes are like built from classical codes. The classical error control coding theory is important. See, it has been important in this computer. SC, DC kind of error correction is already there. But the errors they correct, and they've been brought out to minimize to the range of billion, trillion, 1 in a trillion error is possible. Okay? Now, that's not the stage we are going to reach in any quantum machine from any physics so far. And new physics is being also attempted to say, can we reach 1 in 10 power 9 error rates? The kind of error rates we are used to in this kind of computing. Not so far. And of course, those have been helped by very fast, quick codes. So I will just run through what are called, these are all based on the kind of things which I do for my course, kind of an informal course, research notes and so on. But what will be exciting is to see the intricacies of this codes and why we are motivated by this for quantum cryptanalysis. And why that's probably facing a limitation or a challenge to quantum adversary. So now I am speaking, I'm both an optimist and a devil's advocate. I want quantum computers, I can't escape it to be there, but I don't want quantum computers to break classical things so easily as is being felt, not believed. I'll tell you why. Okay, now there is a history of what goes on in building good quantum error correction codes. It all starts with simple things like classical error correcting codes. Now, there's not too much time to use chalk and board and hours of lectures, but simply I'll tell you, NKD is a standard triple used for a coding metaphor. You'll have a square bracket, N, what are called N symbols, which have K message symbols added with N minus K edit symbols or correction symbols, and which assure you that if you choose N and K and build a code in a certain way, you can decode it in such a way that you can tolerate up to D errors of detection and or correction. That's the idea. Now, the whole world of code, exciting world of code for the last 80 years is about designing such things. And very classical, simple, beautiful codes can be explained the world of what's called as finite dimensional vector spaces. Simple vectors, Boolean vectors, n-dimensional n rows of k columns. Typically, n is much about 2 to 3, 4, 5 small number of times the kinds of classical codes we use. The kinds of quantum codes we use upfront, I'll tell you a ballpark figure, which is the best so far, the best literature so far. I've got about 80 pages of literature, is about 1,000. Okay. Now, how do they work? It all starts with, there is one more thing. So this k bit message bit, you can take k bit. Typically, the first code is 732. That means 7 bits for 3 message bits, 4 bits added, and then it will correct about 1 or 2 errors, roughly. These are all textbook stuff in any coding theory book. So 743, 742, Hamming code, and then on read code, Solomon code, read Solomon codes, etc., and so on. The main point is you need a certain number of control bits so that from the errors when it happens, you can measure the errors and then say this error is a syndrome for that message. You can do that fairly straightforwardly in a simple linear algebraic framework in classical codes. This is the simplest statement. Okay? Bear with me. They're very sophisticated codes. But now you have to extend that 7, 4 to 20, 30. We use 32 bits, machines, words, 64 bits, 64. We want a quadra bit precision, 128 bits. So now we read bigger codes. Okay? So you have, imagine a matrix, n-dimensional, n rows, k columns, n about roughly twice the size of this. This is a code space. Then how you build that matrix is a code design. How you decode is an interesting problem. Now, the decoding is the interesting problem about coding theory, which is central to all kinds of beautiful mathematical research. To say the decoding problem for many codes when the size becomes large is exponentially hard. Bad thing. Okay? But decoding for simple codes with good structures is fast. Okay? So even cryptography is built on this premise that you have an easy problem for the sender and receiver, the same problem appears hard for the adversary who sits in the middle. This is the fun of designing such things. The sender and the receiver, you and me, public key, private key, face certain easy problems because of the trapdoor, whereas the man in the middle faces the hard problem of actually breaking the factory, in the case of IISc. So this kind of design is the fundamental principle of design of all of crypto. So code-based crypto is based on the premise that decoding problem is hard in general, but can be made easy with a little bit of a clue, clues. But of course, the clues have to be buried so that the adversary does not discover the clue. So with all that, the classical decoding for a simple code is a starting point for something called a Pere bit flip code. Now, one little complication arises from now on. There will be many more complications when it comes to quantum world. When the whole business of quantum is some physics which I find it difficult to understand, grapple with. And physicists themselves are difficult people to explain this thing for me to grapple with, and so on. Okay? But apart from that, some simple things. Say, in bits, a bit can toggle error. Of course, it can get lost, it's different, can get squeezed in this another, but it can get flipped. Just one bit. In qubit, this is a very strange world. It's already a superposition of all states, infinite number of states between 0 and 1. It's a continuum. So what does it mean to say something flips? There is nothing like a bit flipping. When you measure it, it falls into a probability that is at 0 or 1, or something like that. Okay? That is for the state of the bit, qubit. But there is something about this quantum world where, because of the quantum mechanical phenomena associated with the physical properties of the material, there is a phase thing. Because there is one of the fundamental things is about spin, and it has some orientations and many other quantum mechanical properties of this. So it's not only that can get into error trap, the actual state of the magnitude, but the state of the phase of the thing also gets flipped. Now, this is somewhat analogous to the modulation scenario in conventional communication. Now, it gets more complicated in the physics world of quantum world. So there is something called a phase flip error. So bit flip error, just 0 or 1, the analogous quantum, whatever it's sitting on, the Schrodinger's cat, wherever it is, when it is measured, it will be either this or this, one way or the other. But besides that, the phase also flips. Now, this phase flip is a nuisance. And so, first starting point, I'll just this and 2 pages of this and then several references about the new codes for quantum world coming from classical world. How do you first design a code? You make it a repetition. See, you have message bits. Now, message bit I used to get sense of a communication. So you have a correction bits. You just repeat that once, twice, thrice. So in quantum qubit correction, bit flip, you can correct by a fundamental 7-3 Hamming code by triplicating the bits. Every bit is represented by 3 bits. So this is the first what's called as a Shor. Shor himself is a code designer. The Shor code line, it's a triplication of a qubit bit flip. And then some classical flipping decoding method works. So in this way, you can complete a simple explanation, not simple, a 2-3 page explanation of a Shor 9 qubit code. Okay, that's one. Now, I have to just give you a few 2 or 3 basic metaphors in quantum computation. So one is the bit flip and the phase flip. Next is, how do these quantum states change? Quantum states change by an evolutionary process in quantum mechanics captured by a linear algebraic framework in what's called as a Hilbert space. Forget about the Hilbert space, but essentially simple linear algebra of operators. Okay, a qubit is a vector. it's a 0, 1 vector of 2 elements. So 2 cross 2 matrices work on them. These are called gates. Okay? There are a set of gates called Pauli gates, under which there is a group system, group theoretic idea, which works on these states. Okay? These are simple gates, okay? X, Y, Z, and then the identity, and so on and so forth. They are supposed to be simple. Let me close to that. Then there is a non so simple, what are called this set Clifford operators, called first name, somewhere you would have heard of this name called Toffoli gate. Now these are like, all these gates are like our classical gates of AND, NOR, XOR, OR. Okay? And then there is a universal set of gates for our conventional computation. But for quantum computation, there is a very difficult theoretic way of saying there is a universal set, but it includes those non-Pauli operator extra gates, which is what gives the quantum power. If it were only these gates, we can simulate the quantum stuff by classical stuff. And then there is no power. The power comes from the other variety of operators which they can work on the quantum states. And I'll leave it at that. So these have been worked upon by people starting from 95. Take a nice, good classical code, see how you can make repetitions and how you can design a code. Now, again, close in a very quick summary, they have to be realized in the physics of things. Here is where you hear some very funny sounding words in the quantum world of codes called magic states. Okay? The ordinary superposed states themselves are quite unintuitive. The magic states are the additional states you introduce by using additional qubits. They will be qubits, but they will also sit with the other qubits to distinguish them. You have to distinguish, by the way. You cannot touch a qubit by measurement. And this is again a fundamental, what's called as a no cloning theorem, the quantum, it's a Pauli exclusion principle, all kinds of things. The moment you touch something quantum, it falls down to classical, which is, we don't know which is correct or not. Okay? So this is the bane of quantum computing. So you can't touch the quantum bit while it is operating, but it may be prone to error. So in order to do the measurement on what's happening, you introduce these additional qubits. They're called ancillary additional. This is where the numerical bottleneck comes into picture. To be able to do things correctly, now you have to introduce many of them, many more of them than in the classical one. That's because of the bit flip and the phase. Two, the more difficult thing which I think physicists and engineers are encountering today is to how to realize them on a kind of a semiconductor-like circuitry in the superconducting world or an ion trap world or a photonic polarization world and so on. Extremely complicated. Of course, they have to lay these qubits in proximity to the data. They're called data qubits, and these are called control or measurement qubits. See, you must know which qubit to touch. It's almost like a very delicate surgery. In fact, there is a thing goes on in something called a lattice surgery, magic state distillation. They all physicists call them. They realize it very, but the basic ideas, mathematical ideas, are quite coming from linear algebra and some Hilbert space theory. So this is how all the code, for example, the toric code is something like on a torus. You build surface patches, you build data qubits here at nodes, put some ancillary qubits here and there, more precisely, wrap them around, join them, cut them, and you can't measure too many far measurements, make near measurements, cut them, make near measurement, join them, all kinds of things. So I'm going to stop just so the references, which itself are forbidding. But anyway, many contemporary codes, which are called low density parity check codes, which are very powerful for decoding quickly if the parity check matrices are not of high density. And how do you design a code such that the parity check matrices are not dense, but the generated matrices will tend to be dense? Okay? Because we want to be that NK ratio to be small. So they will be dense. They're something like a dual. The parity check, which is used to do the syndrome decoding, is sparse. Now, this is a challenging thing in the classical world. It's even more challenging in the quantum LDPC codes. These are some of the latest ones. And last comment is 2025. I've checked there is error correction zoo, which consists of codes in the quantum. About 500 codes are there. You don't ask me why, so it will take a long time to explain. So this is about it. And then there are lots of basics. I'll close the talk. I've already said them. But the basics involves all this. There is a tensor product of Pauli matrices. There are 4. It forms a 16-element group. And unfortunately, many of the important things for quantumness, called Toffoli operations and so on, are not part of that. 3 gates are not part of that. They're outside, but they can be realized and so on. So there are many codes. Lastly, the decoding algorithm, again, some very wonderful classical decoding algorithms, which are very complicated, but quite polynomial time implementable. They call finding paths in a minimum weighted perfect matching in graphs, maximum likelihood decoding, and some kind of machine learning algorithm for decoding work very fast. And the quest is to adapt them to quantum decoding. By the way, lastly, why this decoding has to be done? You can't allow errors to accumulate. Here, you do those things inside the RAMs and the ROMs all the time. And they're extremely fast, okay? And very small. 32-bit, 40, 64, you can do them quite fast. Okay? What's called syndrome decoding by table lookup and all that won't work in these cases. Not only that, the measurements you have to make on them, and then the thing to be done in low scale, small, computation should not be allowed to proceed before the error is correct. Okay? The error correction works in tandem with the quantum computation. This is amazing because, and there is a bit of a drag on each other. Not each other. The quantum computation can proceed immensely fast, which is known because it does the Fourier transforms, everything, polylog time, extremely fast. But the error correction, decoding is a problem. Okay? So decoding should not be a problem. What is this? It's a decoding is a problem, but not a problem. When I say that in the same breath, it means it's a challenge. Okay? So implementing decoding algorithms in tandem with quantum computation so that errors don't accumulate and then you proceed is the big challenge. So lastly, I am more interested in factoring as why it may be done, may not be done. So I think I'll leave all this. I'll give you my motivation for that coming from factoring. This is the latest report from Gidney and team from Google, and who did this in 2019. I've improved it last few months ago. That will be the next stage. See, just read the comments below. There are many codes, surface codes and toric codes and all that, which are, leave that. There is a thing which says RSA 2048, the precision required is 1 in 10 power 17. 10 power 17 is something like, okay, the algorithm sure is very fast. It works in linear time. 2048, 2048. This is 2 to the power of 2048 as a number, but you need only 2048 qubits, not 2048, 2 times n. But the problem is the Toffoli gates go up to cubic or something like that, 10 power 12. 10 power, yeah, something like that. See, 1 in 10 power 18. It's called, if you achieve this. Okay? So this is about 256 million physical qubits are required for RSA 2048. So this is the latest million. No, actually it's been reduced by Gidney. Million is coming from product of kilo. 2048, 2 to the power of 11, 2 to the power of 22, 4 million. So that's about it, what have been improved. And this is the latest. How to factor 2048 RSA integers with less than 1 million noisy qubits. See, the current day machines which have all are noisy qubits. Okay? There is no real error corrected machine in the circuit model or as claimed in the analog model of D-Wave, which will work to millions. Okay? A few hundreds, thousands, it's amazing challenge thing. The 123 IBM machine or something was mentioned. Good, but it cannot solve any of these problems. Okay? And so it's roughly 2n squared, which is 4n squared, where n is that 1 kilo, so million. So you get 2048 RSA integer with less than a million. It's a record of sorts, but this record is amazing. I mean, it's quite intriguingly difficult. It's supposed to be for a superconducting machine, but unlikely to have been implemented for some time. It itself is an improvement of over 20 million qubits in 8 hours. Okay. Anyway, this goes on and goes on. So this game will go on. In particular for this problem, there are other problems it can challenge, solve quickly. Okay? Unwittingly, some hard combinatorial problems like traveling salesperson, graph optimization, are demonstrably solvable in quantum machine by what's called quadratic unconstrained binary optimization, which is inherently hard in classical computing. But quantum, by no theoretical stroke, except by solving large systems of equations, which is unbelievably non-quantum showable to be polynomial time. Meaning, what I mean to say is linear equations solving is not, you don't get too much gain. Quantum advantage is not too much. Okay? But yet, for certain small problems, medium-sized problems, it can solve. Very, very clever ways of doing them in the models of quantum computation. In particular, actually, not on the circuit-based thing, on the analog, what they call the adiabatic evolution machines. Okay. Okay. So this is all about that and how it works. And this has a very messy arrangement of error correction deeply buried inside the solution. If without that, it won't work. And that's the beauty of this paper itself. And it uses very basic that CSS codes, Calderbank, Shor, Sterney codes, which are themselves generalization of classical Hamming code. Okay, so this is it. And so on and so forth. There are many things. I'll just skip all of that. So I want to close always with my, these are descriptions and so on, very quotes. About 50 Gidney's, it's based on what they call yoked surface codes by Gidney himself, who is the author of the Shor improvement and thing. By the way, there are lots of things which are non-Shor, which are also possible to explore. So far, they have not been proven to be good enough, but Shor is not the only answer. So, but then all of them will require error correction of a very high order. Okay. Okay. So these are some projects. Okay. I want to read off my small list of poems. Bear with me. Shor wrote them first. I write verses to whimsical thing. If computers that you build are quantum, then spies everywhere will want them. Our codes will all fail, and they will read our email till we get crypto that's quantum and daunt them. This is Shor and his wife Jennifer in '94, after he invented the algorithm. He said, very difficult algorithm himself to implement because of the other challenges. And Strassen made a poem, to read our email, how mean of the spies and their quantum machine, be comforted though they do not yet know how to factorize 12 or 15. I have seen the factorization of 15 at IISc using NMR spectroscopy and so on. Actually, it was a joke. Not only a joke that it was 15 which was factored, but even to be able to see the answer 15 is equal to 3 times 5 required some bit of understanding. Somebody has to say C3, C5 to see, oh yeah, this peak stands for 3. So anyway, the current day is not much better. About 40 bits of the RSA 2' product have been factored. So lastly, I have been writing some poems, and where we are, I factored RSA 640 in 208 with number field save and the cluster compute of 120 gigaflop years with a cluster of about 400 machines for about 6 months. with number field C, and with CDAC, part of them doing this work here. Unfulfilled wish was RSA 1024 cracked by 2024 with multiple modified in 4 petaflop years. This was my estimate, but we didn't complete the task. Nor the European team. I mean, everybody got bored, left it. 768 is the world record. While superconducting loops, crispy spins, trapped ions, photon alignments are all in a global race lead to useful quantum computing and grand phenomena. I predict an RSA 2048 cracked before 2048 is full of quantum noisy nightmares. We are having noisy base. Anyway, let's hope. I'll stop. Of course, there is a need for quantum error correction. I stop here. So, any 2 questions left for a short time. Let's come back. I can always spend time with you. Okay. Any question of a general or specific kind?
Any question?
Thank you for the session. So the question is very generic, but then when it comes to if the 2048, by the time quantum will be everywhere, that's how the statement ends. Quantum will be there.
Some problem. Can you come?
Yes, yes. Quantum will be there. Quantum computer will be there, and then its quantum computer is going to be there in every field. That's how it says right now. With that, the existing PKI, what we have, the infrastructure existing what we have, whether it will survive as it is, or what are the changes as people who work with security have to take care.
And whenever you are talking about existing infrastructure, where in the world or in India?
Let's say PKI, if we consider.
Okay, very thoughtful thing. I also asked the same question. What can we do with the existing infrastructure in India? As far as I know, there is a public announcement. There is a Bangalore company, occupies IISc, claimed to have a machine of the order of about 13, 14, 15, 16 qubit. See, but if you have a genuine 32 qubit machine, it will be supposedly quantum mechanics wise exponentially faster than this 32 qubit, 32 classical bit machine. All our machines, I'll assume. Okay. Unfortunately, it will not be so because of the lots of other engineering challenges. So, this is what is called as a quantum advantage. It was quantum supremacy, quantum is better, quantum supremacy, quantum advantage to show that it's better than this. If I have to buy that machine for 50,000, I will rather buy this than that machine, 50,000 machine, quantum machine, nothing available. Then quantum utility, it need not be exponentially faster as it is touted to be. Okay? As long as it does it, like he says, 8 hours to factor a 2048, I won't write by a short paper. It should be microsecond if really is done. But it doesn't matter. 8 hours doesn't matter. Morning you start, it will be over by evening. So the short answer is there is no quantum machine which will solve all this problem. On the other hand, the positive side, there are lots of developers tools which are available in Qiskit and Python code which can translate to Qiskit, your conventional algorithms to Qiskit. You can simulate them on conventional supercomputers to some scale. Be satisfied that it may give a little bit of a quantum advantage. If it gives, then send it to IBM. They will run it on their quantum machine and give you the answers. So that's the way the world is.
Thank you, sir.
Okay. Any other question?
Thank you.
Thank you very much, sir. I request Dr. Anand Mohan, sir, to please come on the dais and felicitate Professor C. Veni Madhavan, sir.
Anand and I have been